Let's do some GRE exponents and roots questions. I'm Erika with Target Test Prep, back today with another 3 levels video, this time on GRE exponents and roots. Now, if you haven't seen one of these before, we're going to go through 3 levels of GRE exponents and roots questions. 1 easy question, 1 medium question, and 1 hard question, where the hard question stumps 68% of Target Test Prep students. And I've even got a bonus hard question at the end of the video. If you've seen my video on the hardest GRE Quant questions, then you know that exponents and roots are heavily represented in the most missed Target Test Prep Quant questions. In this video, I'm going to give you multiple approaches for solving each question to ensure you get them right no matter what. Before we jump in, make sure to subscribe for new videos from me every Wednesday. We'll start with the easy question to get warmed up and introduce some key concepts. All right, give the video a pause if you want to try this one on your own. Now, there are a couple potential approaches here. The first is to recognize, hey, in both my numerator and denominator, I'm adding 3 of the same thing. So in my numerator, I'm adding 3 2 to the 14ths, and in my denominator, I'm adding 3 2 to the 12ths. Now, if we had something like x plus x plus x, we would immediately combine like terms for 3x. And if we had something like x squared plus x squared plus x squared, again, we would hopefully immediately combine like terms for 3x squared. Well, we can do the same thing here. If we can do it with variables, we can do it with real numbers. So I can express adding my 3 2 to the 14ths as 3 times 2 to the 14th. And I can express adding my 3 2 to the 12s as 3 times 2 to the 12. From here, I can cancel my 3's, which is going to leave me with 2 to the 14 over 2 to the 12. Now, using my quotient rule, I know that when I'm dividing 2 terms with a common base, like 2, I can combine by subtracting their exponents. So that's going to give me 2 to the 14 minus 12, or 2, and 2 to the 2 equals 4. My correct answer is B. Now, if the combine like terms approach didn't occur to you, there is another approach, which is to treat this the way we would treat most problems where we want to simplify the addition of terms that for some reason we can't add, whether that's because they aren't like terms or because they're simply too large, as in this problem, and that is to factor. So in my numerator, I can factor out a 2 to the 14, leaving me 1 plus 1 plus 1 in my parentheses. Same approach in the denominator. I can factor out a 2 to the 12, again leaving me with 1 plus 1 plus 1. Simplifying a bit, I have 2 to the 14 times 3 over 2 to the 12 times 3, which is exactly the same thing that we had before, just arranged slightly differently. So at this point, I would do exactly what I did before, simplify by canceling out my 3's and then applying my quotient rule to get 2 to the 2, or 4. Answer choice B. And there's even a slightly different factoring approach, which is to factor out a 2 to the 12 in the numerator instead of factoring out a 2 to the 14, which allows me to, again, factor out a 2 to the 12 in the denominator, giving me a 2 to the 12 in the numerator and the denominator that we can cancel, which leaves me with terms that are small enough to calculate. So I have 4 plus 4 plus 4 over 3, that's 12 over 3, or once again, 4. Answer choice B. So a lot of approaches that all boil down to our exponent quotient rule and the manipulation and simplification of expressions. Let's ramp up the difficulty a bit with the medium question. Once again, pause the video if you want to try this one on your own. Okay, at first glance, this one looks pretty overwhelming. We've got a fractions within a larger fraction situation. However, we can pretty quickly get this one at least looking more manageable by remembering that dividing by a fraction is the same as multiplying by its reciprocal. So we can rewrite this as our fraction numerator, so 1 over 2 to the x plus 2 to the x minus 1, times the reciprocal of our fraction denominator. So that's going to be 2 to the x plus 1 minus 2 to the x over 1. All right, from here, multiplying is pretty straightforward. We're going to get 2 to the x plus 1 minus 2 to the x all over 2 to the x plus 2 to the x minus 1. Okay, this is less visually overwhelming, but we've still got a ways to go. Now, just like in the last problem, we've got the addition and this time subtraction of terms we cannot add or subtract. Now, since these are not like terms, we are probably looking at factoring. If you're a whiz with factoring exponents, you might immediately see what to do. But if not, we're going to take an intermediate step, and that is to work with our more complex exponents. Now, we see that these complex exponents involve addition and subtraction. Well, when do we add and subtract exponents? When we multiply and divide terms with common bases. So when applying our product and quotient exponent rules. So what if we worked backwards and applied our rules in reverse? So 2 to the x plus 1 has addition in its exponent. So it could be formed by multiplying two numbers with a common base, in this case, 2. So 2 to the x plus 1 can be rewritten as 2 to the x times 2 to the 1. Now, if you're not convinced, you can prove it to yourself by applying the product rule in the normal direction. So we have a common base of 2. We are multiplying, so that means we can add our exponent. So that would give us 2 to the x plus 1, which is what we had before. This is valid. All right, continuing on with my math, I'm going to do the same thing to the complex exponent in my denominator. So my denominator has 2 to the x minus 1 in it. Now, rather than use my quotient rule and introduce another fraction, I'm going to instead treat this as 2 to the x plus -1. And this is going to allow me to apply my product rule in reverse again for 2 to the x times 2 to the -1. Now, you absolutely don't need to do this. You can use the quotient rule in reverse instead, and you will get the same answer. This is just a little bit cleaner for the whiteboarding process. Now, you might be thinking, why would I work in reverse? This seems like a step in the opposite direction, like I am complicating rather than simplifying. Well, let's look a little bit closer because now I can very clearly see what was true all along, which is that I have a common factor of 2 to the x in all four of my terms. So I can factor out a 2 to the x in my numerator, giving me 2 to the x times 2 to the 1 minus 1. And I can factor out a 2 to the x in my denominator, giving me 2 to the x times 1 plus 2 to the -1. From here, I can cancel out my 2 to the x, and I can simplify my terms a little bit. So I'm going to have 2 minus 1 in my numerator and 1 plus 1/2 in my denominator. So I have a negative exponent. That's going to mean that I take the reciprocal of what it would be with a positive exponent. Okay, so I have 1 over 3 over 2 multiplied by the reciprocal of the denominator is 1 times 2 over 3 or 2 over 3. My correct answer is C. Now, if any of those steps felt unapproachable, whether that's the fraction rearrangement at the beginning or the application of our exponent rules to factor, once again, there is another approach, and that's going to be picking numbers. So for this problem, that means picking a number for x. Now, I'm going to pick a number that's going to be easy to work with and not introduce anything weird. So I'm going to go with x equals 2. So plugging in x equals 2, that's going to give me 1 over 2 to the 2 plus 2 to the 2 minus 1. And all of that is going to be over 1 over 2 to the 2 plus 1 minus 2 to the 2. Simplifying just my complex exponents, I'm going to have 1 over 2 to the 2 plus 2 to the 1 over 1 over 2 to the 3 minus 2 to the 2. Now, because I intentionally picked a small number, I don't have to apply any exponent rules or factor. I can just calculate. So I have 1 over 4 plus 2 over 1 over 8 minus 4. Continuing, I have 1 over 6 over 1 over 4. From here, multiplying by the reciprocal of my denominator, I have 1 over 6 times 4 over 1. Multiplying across, 4 over 6, which reduces to 2 over 3. Once again, the correct answer is C. So, like in the last problem, there are multiple approaches, all based around algebraic principles that can help us get around the trickier applications of our exponent rules. Ready for the hard question? This is one of the most missed questions in the Target Test Prep course, with less than a third of test takers getting it right. You know the drill. Pause the video if you want to give this problem a go on your own. Now, just like in our previous questions, we are being given an expression that equals one of our answer choices. But in this problem, we have roots instead of exponents. Well, no worries. We know that roots are just fractional exponents. The square root of a is just a to the 1/2. So that means that we can apply all of our fun exponent rules here as well, of course, bearing in mind any interactions with negative numbers. Well, at present, there aren't really any places to apply our exponent rules. Like in our previous questions, we have a bunch of addition and subtraction that we can't execute, but unlike in our previous questions, there aren't any fun ways to factor. There aren't any like terms, there aren't any variables we can pick numbers for, so none of the tricks we deployed in our other expression problems are gonna do the trick. Well, here's another fun trick. If you find that manipulating your expression is inadequate to solve, turn your expression into an equation. So instead of trying to manipulate the square root of 12 plus 2 times root 11 minus the square root of 12 minus 2 times root 11, you can set that expression equal to x, where x is the thing that we are solving for. It is our answer. And then we can manipulate this equation. Now, there's only so much you can do to expressions, but when you have an equation, you gain an extremely powerful tool, and that's doing the same thing to both sides. Now, of course, you have to be careful when you're working with a variable you don't know the value of. For example, in a problem with square roots like this one, we would need to treat our solving differently if our answer could be a negative number. Fortunately, here it cannot be. If 0 were a potential answer choice, I'd need to be careful with division, etc., etc. But the potential upside of doing the same to both sides is huge. So with my new equation, I can now do something to both sides to materially change my expression. Well, I'm dealing with square roots. Let's square. Now, critically important, we need to ensure that we distribute our square across this subtraction. Now, if we are fluent with our perfect squares, we know that a minus b squared is going to equal a squared minus 2ab plus b squared. Applying that here, we're going to have x squared equals the square of our first term. So that's going to be 12 plus 2 root 11 because squaring gets rid of that square root. Then we're going to have minus 2 times our first term, root 12 plus 2 root 11, times our second term, root 12 minus 2 root 11, plus our second term squared, or plus 12 minus 2 root 11. Again, squaring is going to get rid of that broader square root. And if we are unsure about any of this, we can always FOIL. So first, outside, inside, last, and that's going to give us the exact same thing, just with a little more time investment. Okay, now we are getting somewhere. Let's start simplifying. So this plus 2 root 11 and this minus 2 root 11 are going to cancel. And then we can add our two 12s to get 24. Okay, in this big term, we see that we have two square roots multiplied by each other. Now, when we have two square roots multiplied by each other, we can multiply what's inside them and combine under one big square root. Now, this is my power of a product rule, just applied in reverse and applied to a fractional exponent or a root. Kind of complicated. Now, we may have noticed earlier in the problem that we had the makings of a difference of squares here, and that is finally coming to bear. So we know that a squared minus b squared is going to be equal to a plus b times a minus b. And that is exactly what we're going to have here under this big square root. So applying that here, we're going to have 12 squared minus 2 root 11 squared. And again, if you don't notice the difference of squares, you can again just FOIL and you'll get the same thing, just a little slower. All right, working at this a little bit more. The square of 12 is 144. Applying my square across both of these terms is going to give me 4 times 11. Super important to distribute that square. Continuing on, I'm going to see that 4 times 11 is 44. So I'm going to end up with 144 minus 44, or 100 under this square root. Our math is looking really clean, which is a very good sign. The square root of 100 is 10, so we're going to end up with 24 minus 2 times 10, which is 20. So x squared is going to equal 4. Now, important, 4 is not our answer. We have to remember we are not solving for x squared, we are solving for x. That is what we set our original expression equal to. So we are going to need to square root both sides. All right, this is going to give me x equals plus or minus 2. Now, importantly, -2 is not an answer choice, and if we were to check back with our math, with our original expression, we are going to see that it doesn't actually make sense that our answer would end up negative. So the correct answer is going to be +2, or answer choice A. And just like in the other problems, there is another approach, and that's going to be estimation. We can use close by perfect squares to approximate the value of our various roots and solve for an approximate answer, which we can then compare to our answer choices. Now, looking at our answer choices before we start in, we're going to notice that a lot of them are pretty close in size, so we're going to want to be pretty precise with our estimations. All right, first step is going to be approximating root 11. Now, the closest perfect squares to 11 are going to be 9 and 16, which means that the closest integers to root 11 are going to be root 9 and root 16, or 3 and 4. Now, 11 is much closer to 9 than it is to 16, which means that root 11 is going to be quite a bit closer to 3 than it is to 4. So I'm going to go ahead and estimate root 11 at 3.3. So we're going to have the square root of 12 plus 2 times 3.3 minus the square root of 12 minus 2 times 3.3. Doing that multiplication, we're going to get the square root of 12 plus 6.6 minus the square root of 12 minus 6.6. And then executing that addition and subtraction, I'm going to get the square root of 18.6 minus the square root of 5.4. Okay, time for more approximation. The closest perfect squares to 18.6 are going to be 16 and 25. So the closest integer square roots to the square root of 18.6 are going to be 4 and 5. Now, 18.6 is, again, quite a bit closer to 16 than it is to 25, so the square root of 18.6 is going to be closer to 4. I'm going to approximate this one at 4.3. Moving on to our next term, the closest perfect squares to 5.4 are going to be 4 and 9. So the closest integer square roots to the square root of 5.4 are going to be 2 and 3. As before, 5.4 is quite a bit closer to 4 than it is to 9, so the square root of 5.4 is going to be closer to 2. I'm going to estimate this one at 2.3. Doing the subtraction, I get 4.3 minus 2.3, which happens to be exactly 2, or exactly answer choice A. But even if you estimate slightly differently, as long as you're not really far off, you're still going to get an answer choice close enough to 2 to feel confident picking A as the correct answer. So 2 approaches, 1 algebraic using our exponent and root rules, and 1 more arithmetic that allows us to get around our exponent and root rules altogether. Now, of course, these are just 3 questions. There are a lot of exponents and roots concepts that we didn't cover here. Zero exponents, power of a fraction, scientific notation, the one-to-one property, and so on. But as we proved with these problems, knowing and applying exponent rules is only part of the puzzle. Like with most math problems on this test, a strong foundation in algebraic and arithmetic principles and a flexibility in your problem-solving approach can get you a long way. To be clear, I'm not saying don't memorize and practice your rules. You will need to use them. But remember that these problems are designed to test critical thinking, and use that to your advantage. If you want to challenge yourself, here's another hard exponents and roots question that 65% of students get wrong. Give it a shot, and if you're brave, comment your answer below. If this video helped you, throw us a like. Thanks for watching, and I'll see you in the next one.